What is the shortest path problem? So we're given a graph G, that is, we're given a vertex set and edge set, a set of nodes and a set of links. And it is a weighted graph, so each link has a certain number, a weight associated with it, interpretable as the cost of using that link. And it's a directed graph, so node I goes to node J doesn't mean that node J also goes to node I. And our job is actually very simple. We just want to find a minimum cost path. There might be multiple. We just need to find one between each pair of source and destination. Okay, so that's a very simple statement, and it turns out this is one of the most extensively studied graph theoretic optimization problems. It's got the name the shortest path, which is a little misnomer, because the best name really should be minimum cost path problem. Of course, if the cost is the physical distance, then a special case is shortest distance. And if the path link cost is actually all one for every link, then this is basically a minimum hop count path problem. So how can we solve this problem? There's so many different nice ways. We will look at a specific one based on the dynamic programming principle, or the so-called Bellman equation. If you are taking an optimization course, you probably will spend quite a few lectures on dynamic programming. Okay? But here we just illustrate it in one specific algorithm. Again, notice that we're given the graph G, and for each link there's a cost Cij for link I to J. And the main idea behind this Bellman's equation and the resulting Bellman-Ford algorithm was the following. If you are node I, okay, and you have a destination N, you want to figure out the best way to get there, the shortest path, or the mean cost path. Okay. Well, you have to get there from one of your outgoing neighbors. There should be an arrow here. Say you've got 3 neighbors. So whatever path you take, you have to first start with one of the 3 neighbors. Okay? And there's a cost of going to the neighbors, Cik here. Then let's denote by P sub I t as the minimum cost it takes for node I to go to destination N from I to N. Let's assume this N is a common fixed N for everyone. Okay, so we just suppress the N notation here with an implicit understanding that we're talking about destination being node N. So this is the minimum cost for source I to go to N using T or less hops. You think, but T, we usually reserve that index for time, and indeed we can view this as the iteration index over discrete time slots as well. Okay, you both have a temporal meaning over iteration as well as a spatial physical meaning here. So using that notation, we can write down the following obvious statement. For example, at time 0, every node takes infinite cost because you cannot get to the destination using 0 or less hops. Okay? Unless node I is node N itself. You are the destination yourself. Then in that trivial case, yeah, you're already there. And we can also write down, therefore, at whatever time or whatever number of hops you may need, you can always get to yourself with 0 cost. Okay, so these are just obvious statements using this definition of the notation PIT. Now here comes the somewhat magical part. We want to find out PI, let's say using T plus 1 or fewer hops. That means we have to go through, well, one of the outgoing neighbors indexed by K, okay, with a cost Cik. Then once you get to that neighbor, one of these neighbors, you've already used up 1 hop. So you need to get to that destination with T hops or fewer. And if you could know still a if at this point, the minimum cost it takes for node K, that's the neighbor you just picked, to get to destination and using T or fewer hops, then that's great, because you can then add these two up. Now the question is, which outgoing neighbor K to pick? Well, I'm going to pick whichever one can give me the smallest sum. So pick the mean of the sum over all the nodes indexed by K. That's your outgoing neighbors. This is the famous Bellman's equation. And we can indeed rigorously prove that this equality holds. Now, this Bellman's equation is useful for an algorithm only if you can actually efficiently compute pkt. Then you can compute pit plus 1. But can you compute pkt efficiently? Well, let's use the idea of recursion. So using recursively this Bellman's equation, you can keep writing this from t plus 1 to t minus 1, t minus 2, all the way down to 0. Then you see that no nodes can get to destination in 0 or fewer hops except the destination itself. And then you can recursively work your way back to t plus 1. We're going to illustrate this whole process in an example numerically in a minute. But this is the famous Bellman-Ford algorithm. Okay, essentially it is an algorithm for efficient computation following this Bellman's equation. Notice the min is taking over only those nodes K that are your outgoing neighbors. So this is one of those beautiful, elegant, and yet extremely useful and so often used equations, like those we encountered in lectures 1, 2, and 3 back then. Okay. So without going into the underlying dynamic programming principles, because then we'll be dragging sort of off the track a little bit, let's take a look at an example that illustrates how this can be computed, at least centrally. Okay, suppose you actually know the whole graph. How can you compute this centrally? Then we'll look at, in the next module of the video, the distributed version, where no one has a global bird's eye view of the whole graph. Then how can you implement this computation? Okay. So here's the centralized example. This is an extremely small graph. For such a small graph, you can probably just eyeball the answers. Please don't eyeball the answer. Let's follow the Bellman's equation, because the purpose is not to really find the shortest path in this graph. Who cares? Is to illustrate the Bellman-Ford algorithm. Okay, so notice in this graph we got A, B, C, D, 4 nodes, 5 nodes. There's also a common destination node N. We can do all to one routing, basically. Okay, find out all the shortest path from these 4 nodes to common destination N. We could also do one to all, following a similar procedure. Okay, so you look at these link weights, which are the numbers written next to the directed weighted links in the graph. You see, hey, there are some negative numbers. What do you mean by negative weights? There are 3 negative numbers. Well, it's really for generality's sake. It may have some physical meaning in certain contexts, but for this purpose, we just want to show that it's okay to have negative weights on a link for Bellman-Ford to still work out, as long as you don't have no negatively weighted cycles. Cycle is a path, concatenation of links that ends up where it started. Okay, so for example, C to A to B to C, that's a cycle, right? It's a concatenation of links, 3 links, and then you end up where you started with. And the total cycle path is -2 plus 8 plus 4, which gives you 10 as the cycle weight, which is positive number. So as long as you don't have a cycle with total negative weight, then it's okay. What's wrong with a negative weighted cycle? Well, because if this whole cycle is negative weighted, then you can just keep going, looping this infinite number of times. Then it'll push your total cost down to infinite. Okay, before you take one more hop to get to the destination, or two more hops. So no negative cycles, otherwise the problem is ill-defined. Negative weighted links, that is okay. All right, so let's run the Bellman's equation now. At time t for this graph, just remember that graph now. Okay, we have the following: PA at time 1. Okay, this is t equals 1. By Bellman's equation, is the mean of the cost from A to B, and then the mean cost from B to the common destination N, suppressed in the notation from the previous iteration, or using one fewer hop, that means use 0 hops. Okay. Or go through neighbor C, or go through neighbor D. What are these three numbers? Well, it's 8 plus infinity, 6 plus infinity, and 4 plus infinity, because the previous iteration, they're all infinity, and this is infinity, which means you have no way to get from node A to the destination in the first iteration, i.e. using one or fewer hops, which is obviously true. It's trivial. Of course, A is separated from N by 2 nodes. By one node, so you at least need 2 hops to get to N. But again, don't eyeball the solution. We just want to illustrate Bellman equation using as simple a numerical example as possible. Similarly, you can write down PB at this time iteration is also infinity. What about PC? Actually, PC is not infinity anymore, because it's the mean of 3 numbers, 6 plus 0, if you go through node N directly, minus 5 plus infinity if you go through its outgoing neighbor D, and minus 2 plus infinity if you go through its outgoing neighbor A. But clearly, you want to pick the first one. That's 6. And PD, similarly, you can find to be 7. So it's infinity, infinity, 6, and 7. And iteration 1. Okay, using 1 or fewer hops. Now let iteration 2 starts. You can now see suddenly that PA at 2 is not infinity anymore. It is the mean out of 3 choices of its outgoing neighbor. Through B, you get A plus infinity, because it's still infinity in the last iteration. PB at iteration 1 is still infinity, so it's A plus infinity. That's no good. But then you got 6 plus C's, no C's. Minimum cost last iteration using 1 of your hops, that is 6. Very good. Then you got 4 plus 7 if you go through D. Now clearly the mean of that is 11. 4 plus 7. Go through neighbor D. You should write on a separate sheet of paper what exactly node are you using. Okay, this is purely computing the shortest path, but obviously you can also trace back the actual path itself, in addition to the cost of the shortest path. Good. So PA now is 11. Following similar calculation, PB now is 3, and PC now is 2. You can easily derive this yourself or see in the textbook. What about PD? We're going to stop writing PD because PD is boring. D has only one outgoing neighbor, which turns out to be the destination itself. So it will always stay the same number, which is 7. Okay. So now it becomes 11, 3, 2, 7. Keep going. Iteration 3, you see that PB, iteration 3 is now the mean of what? 8 plus what? What does it take for node B to get to the destination? 3. Okay, very good. 8 plus 3. Okay, 6 plus 2, 4 plus 7. Notice the last iteration's updates into 11, 3, 2 are reflected here. Now you've got 3 and 2. Okay. So now this is 7, and similarly PB at this iteration is minus 1. Oh, I'm sorry, not 7, this is 8. Okay. minus 1, and PC is 2. Okay, PD again remains the same. Keep going. T equals 4. Okay, PA now is, you can compute 7, PB is minus 1, PC is 2, PD is still the same. And how about we keep going? T equals 5 equals 6 and so on. Turns out we don't need to do that. There are two ways to look at it. One is it no longer changes. Okay, you can try it, but you will see that it no longer changes. You have converged the Bellman-Ford algorithm at the right answer. And second, if you actually had a bird's eye view and know how many nodes there are, you know there are 4 nodes, okay, other than yourself out there. So you got to be able to stop at iteration 4. You know this a priori, because if you keep on going any further, I say, well, I give you 1 more hop. You can go up to 5 hops or more, or fewer. You can go up to 100 hops or fewer, not just 4 hops or fewer. Say, I don't care. It doesn't help me anymore. Why? Because the only way for me to leverage beyond 4 hops is to actually go through the same node twice, because there are only 4 other nodes out there. And therefore, I will have to go through a cycle. But I know cycles are not negatively weighted, so it will add to my cost. No cycle is needed, so I don't need to go beyond 4 hops or more. Either way, you know, you can stop. And this illustrates the Bellman-Ford algorithm, but it does not show you how to do it distributedly.